Okay, finishing up chapter 4. We talked about acid-base titration. We can also do a redox titration. Remember redox, oxidation, reduction, oxidation. What are we doing? No, oxidation, we're doing what? Something with electrons. Are we gaining them or losing them? Leo the lion says grr. Oxidation, LEO. Losing. Loss of electrons is oxidation. So gain of electrons is reduction. So we can use that reaction to do what's called a redox titration, because we're going to have, in this case, one reactant being delivered by a burette. Burette is the tall thing that's graduated with the stopcock, which you're going to use later on to do titration. So here, this common type of redox titration, we're going to use a solution of potassium permanganate. Remember acid-base, we had to have an indicator. Well, potassium permanganate, which is an oxidizing agent, happens to be a dark eggplant purple. I don't know if it shows you a picture of it. And you can see it up in the burette. MnO4, it's dark purple. So here we're adding it to a solution of sodium oxalate. So as it oxidizes, the purple color disappears. So that's why you see it clear as you're adding it. Once you oxidize all the sodium oxalate, the next drop is going to not have anything oxidized, so it's going to stay purple, and it'll turn the solution pink. So that's how you know you've reached the end point. So the reaction is 2 permanganate ions react with 5 oxalate ions, and you have some acid in there. And we get 2 Mn2 plus, 10 CO2, 8 H2O. Let's kind of look at what's going on in a redox. We have MnO4 minus. We're just going to look at the Mn's. So we have, that goes to Mn2 plus. And the other thing that's changing, we have the C2O4, 2 minus. The carbon's going to CO2. What's the oxidation state of manganese in MnO4 minus? Don't look it over there, just look at this. What's the oxidation state of oxygen normally? 2 minus. How many oxygens do we have? So how many minuses do we have? 8. So Mn, the manganese must be? No, what's the total got to add up to? -1. So it's going to be 7 plus. Always look to see if there's a charge. So here we have manganese at 7 plus. What's it over here? So how does it go from 7 plus to 2 plus? There's a lose 5. Electrons are negative. Gains 5. So this is going to gain 5 electrons. Here in the oxalate, we have C2O4 2 minus. So we said the oxygen was -2. So this is -8. What? And it's got to add up to 2 minus. So the carbon's got to be 6 plus. And there's 2 of them. 3 plus. Over here, this is minus 2, so it's minus 4. The carbon here is what? It's got to add up to 0. So the carbon here has got to be what? 4 plus. So the carbon is going from 3 plus to 4 plus. How does it do that? Loses an electron. So since the carbon is losing an electron, what's happening to it? It's being oxidized. The manganese is gaining electrons, so it's being reduced. It's got to be the opposite. So which one is the oxidizing agent? The manganese, because it's being reduced. And then we say at the beginning of this problem that permanganate was the oxidizing agent. So that should be a clue right there that it's being reduced. So here's another problem, sample problem. Vitamin C ascorbic acid. And there's the formula for it. Content of Gatorade and other sports beverages can be measured by titration with iodine solution. So there's the equation, I2 there's the iodine plus the ascorbic acid, C6H8O6 goes to 2I minus plus C6H6O6 plus 2H plus.
Oh, I'm right.
Okay. No, that's fine. I thought maybe I made a mistake. Yeah, so determine the mass of vitamin C in milligrams contained in 350 milliliter bottle of Gatorade if a 250 milliliter sample requires 29.25 mils of 0.00125 molar iodine solution to reach the endpoint. Oh, here's where your eyes bug out, right? So we know the molarity of the iodine solution is 0.00125. And how much of it do we need? 29.25 mils. Molarity. And we had, what was it? 25 mils of the Gatorade. So 25 mils of this. How much is in a 350 milliliter bottle? Molar mass of vitamin C is 176.1 grams per mole. We use 29.25 mils, so it's 0.02925 liters. We're going to go through it the way they did, and I'll probably show you an easier way to do it. So we take, remember, molarity is equal to moles of solute over liters of solution. So we have the molarity, 0.00125. We converted this to liters, 0.00125. So to figure out the moles, it would be the molarity times the liters, is what they did up there. So we have 3.656 times 10 to the minus 5th moles of iodine. Well, if we look at the reaction, what is the relationship between iodine and ascorbic acid? How do they react? What are the coefficients in both cases? So they react 1 to 1. So if I have 3.56 times 10 to the minus 5 moles of iodine, how many moles of ascorbic acid did I use up? The same amount. So I have, well, you read it, 3.56 times 10 to the minus 5 moles of vitamin C. So now I know how many moles of vitamin C I used. That were in that 25 mils. So I go to the mass, moles to mass, again, stoichiometric roadmap. It turns out to be 6.44 times 10 to the minus 3 grams. Or 6.440 milligrams of vitamin C. What was the volume of a solution that we titrated? 25 mils. So how much is in the 350 ml bottle? Turns out to be 90 milligrams. It's that much in 20, you just set up a ratio. That's 25, how much is in 350? Okay. So that's one way of doing it. So you remember when we do titrations, it was the molarity of the H plus times the volume of the H plus is equal to the molarity of the OH minus times the volume of the OH minus. Well, instead of this is for acid base, I could change this to be the molarity of the iodine times the volume of the iodine is equal to the molarity of the ascorbic acid times the volume of the ascorbic acid. Well, the molarity was 0.00125. We had 29.25 milliliters. The molarity of the ascorbic acid, and we had 25 milliliters. So then the molarity of the ascorbic acid, solve for that. 0.00125 times 29.25 divided by 25, 1.46 times 10 to the 20. How do we do that? Did I make a mistake somewhere? Should, yeah. Should come out to be the same number. Oh, that's the molarity. 0.001462 molar, which is moles per liter. And I can multiply it by the number of liters. Figure out the number of moles we have. So this is moles per liter times 0.025 liters, which is 25 milliliters. And I get 3.656 times 10 to the minus 5th. Moles, which is what I have up there. Or instead of using the 25.025, I could use 0.350 and gone directly to how much was in the bottle. And then convert that to milligrams, grams and then milligrams. Does there's more than one way of doing it. But the concept is the same. It reacts 1 mole to 1 mole. You know how many moles you start with. You have the molarity and the volume, you know how many moles. And then you know how many moles of the other one you have. Then if you know how many moles of the other one you have and the volume, you can figure out its molarity, and you can figure out its weight from the moles. Okay? Now, does anybody think about it? And that was the end of that.